Welcome to Chemistry Lover, and this is the third part of the reaction of carbonyl compound. And in this video, I am going to talk about nucleophilic substitution reaction of carbonyl compounds. So let's start our today's topic. So in the previous video, I discussed that when you have a carbonyl compound and you have a nucleophile, the nucleophile will readily attack on the carbonyl group at the pi star orbital to give you some intermediate like this. Okay, now when we had only R groups like alkyl group or hydrogen in case of aldehyde, it simply takes a proton from the medium and it will give you product like this. Okay, and this nucleophile, we have seen that alcohol can act as nucleophile, cyanide can act as nucleophile, and based on that you will get different products. But here we are going to discuss about substitution reaction. Now when substitution reaction takes place, so let's say you have a substrate where you have a leaving group, for example chlorine, in your carbon atom, and then let's say you react it with some organometallic reagent like Me, MgBr, the Grignard reagent. So what will happen? The Me group will attack over here because Me minus is a nucleophilic species and it will open this carbonyl group. So basically the pi star attack will take place and you will have this kind of intermediate. Okay, now here you have the methyl. Now there is a difference between this and this. Why? Because this is called the tetrahedral intermediate. What is the tetrahedral intermediate? When your compound has a carbon atom which contains two electronegative groups like oxygen with another oxygen or chlorine, bromine, like that, it is called tetrahedral intermediate. So when same carbon contains two electronegative groups, it is called tetrahedral intermediate. And tetrahedral intermediates are not stable, they are unstable, because if this oxygen O minus push its electron, this chlorine can easily leave to give you this substitution product over here. Now chlorine here is a leaving group. Now what is the difference between this and this? In this case you have only R group, methyl or any other R group, and they are not leaving group. But here presence of chlorine makes it a substrate for a substitution reaction, because chlorine is a good leaving group, Cl minus, and that's why tetrahedral intermediates are not stable. Similar reaction takes place when you have ester. So when you have ester and if you react it with MgBr, what will happen? This Me will attack over here, and we generally represent it like this. So this O opens and it closes, and this OR leaves. So here the leaving group is OR minus. So like Cl minus, OR minus is a quite good leaving group, and in this case also you will get the substituted product. So this is the general mechanism of nucleophilic substitution reaction at the carbonyl group. So let me draw the mechanism in a summarized way. So if I draw the mechanism in a summarized way, how it will look like? So you have a carbonyl compound which contains a leaving group X, and you have a nucleophile. So what happens? Your nucleophile attacks over here. This O minus opens, again it closes, and this X goes. So you have this substituted product, and X goes as leaving group. So this is the summary of mechanism of nucleophilic substitution reaction at carbonyl carbon atom. Now let us revisit one reaction which we partially discussed in the last video. So what is that reaction? So that reaction is basically the hemiacetal or hemiketal formation. So we have seen that when you have ketones and if we treat this with alcohol in presence of acid, we get this species, right? And this is called hemiketal. When we have a hydrogen group in presence of R, it is called hemiacetal. Now this is a reversible reaction, but actually the reaction is not stopped here, and it can go further. How it can go? So this OH group, it can again take up a proton, and if it does so, you will have this OH2+, right? Now you can see this is a tetrahedral intermediate, because if this oxygen lone pair push, this can go as water. So again, this is a reversible step, and in this step water can go H2O, and you will get this species, which is a kind of intermediate, right? So this is another intermediate, and again you have lot of alcohol molecules present in your reaction mixture. So any of the alcohol now can easily attack over here, and from this you will get this RO dash OHR. So this new alcohol here will have positive charge, and this finally when it loses its proton, you will have this OR dashed, and here you have, so here you will be R dashed, right? So this is R dashed, yeah. So this is now called ketal. Similarly, if you use aldehyde, it will be called acetal, right? So acetal or ketal is formed where two equivalents of alcohol is added to the carbonyl compound. Now, if you have a alcohol where you have two OH group, that is diol, then you don't need two equivalent of alcohol. So simply, if you have this kind of carbonyl group, carbonyl compound, and if you have this diol species, if you do acid catalysis, you will get this. So now only one equivalent of your alcohol is sufficient, because you have two OH groups in the same molecule. So try this mechanism by your own. Now this is acetal formation, and this mechanism, whatever I have shown of acetal formation, is very important. You should practice this well, because it will help you in many other reactions. Now the next substitution reaction which I am going to talk about is the esterification reaction and the ester hydrolysis. So if you have a carbonyl carboxylic acid, and you treat this with H plus and alcohol like R dash OH, any alcohol, it may be ethanol or methanol, anything, then you will form ester, OR dash. So this is how ester is formed. Now this reaction is reversible, and this ester can be hydrolyzed in presence of H plus and H2O to give you this carboxylic acid back. Now this ester hydrolysis can also be done with NaOH, sodium hydroxide, that is alkaline solution. But the reverse is not true. You cannot do this reaction with base catalysis and alcohol. So we will see later that why it is not possible. But now first we will see the mechanism of esterification. So it is same as it is similar like the acetal formation. So what happens first is you have this carboxylic acid, and in presence of acid medium, this carbonyl group can be protonated to make this center more electrophilic, right? So this center becomes more electrophilic, and now alcohol molecules present in your reaction medium, it will attack over here. So this will open, and from here you will get this OH, and here you have this OR dash H plus, right? And all these steps are reversible. Now proton exchange can occur between this group and any of these two groups. So that will give you OH2 plus over here, OH over here, and here you have this OR dash, right? And here you have this R. Now when this oxygen lone pair pushes, this OH will go as H2O, and here you will have, after deprotonation, here you will have this ester. So this is how esterification takes place in acid catalysis reaction. Now again, this ester can be hydrolyzed in acid or base to give you this. This ester can be hydrolyzed in acid or base to give you this carboxylic acid back. And there are several mechanisms of acid ester hydrolysis. There are many classes, 7 to 8 classes. So that's why I will discuss them in the next video. So I will end this video here. If you like this video, share this video with your friends, and also let me know in the comment section. Thank you for watching.